Moving on to section 11.4, in this section we're going to take a closer look at the phases of matter and the transitions between those phases. When we say a phase, we mean a physical form of a pure substance. So that might be a solid, a liquid, or a gas. We'll see by the end of this lecture there's even another state called a supercritical fluid. But these are things that you should be familiar with. For just about any substance, there's only one liquid phase, and for every substance I know there's only one gaseous phase, but it's worth noting that some substances can have more than one type of solid phase. For example, if we think about carbon, we can identify the diamond form and the graphite form, and these two are different from one another, and one can have phase transitions from one solid phase to another solid phase. Here on this slide we see some familiar transitions. For example, the picture shows the water being boiled. Okay, so that would be a transition from a liquid state to a gaseous state. And here we see this chunk of carbon dioxide. Sometimes you might call it dry ice. Carbon dioxide has a property where it goes directly from the solid state into the gaseous state. Okay, this diagram shows the vocabulary associated with phase transitions, as well as the relative energies of phase transitions. So if we start with something as a solid, perhaps water is the best example to keep in mind. If we add heat, we can transform the solid ice into liquid water. All right, we call that melting or fusion. We've got a red arrow here because that is an endothermic process. We have to add heat to the water to drive this transition. If we go from the liquid state to the gaseous state, we might, in everyday vocabulary, call that boiling, but the name of the phase transition is vaporization. It's also possible, like carbon dioxide, to go directly from the solid state to the gaseous state, and that's called sublimation. And those three phase transitions are all endothermic. Their reverse processes, the names are also shown here. From the gas to the liquid is called condensation. From the liquid to the solid is called freezing. And from a gas directly to a solid is called deposition. These processes, being the opposite, are going to release heat, and so they will be exothermic. Each of the phase transitions that I showed on the last slide has a certain energy associated with them. For example, if we think about melting or fusion, there is a certain enthalpy associated with that transition, which we could call the enthalpy of fusion, delta H fusion. It's also commonly called the heat of fusion. And by the same token, we have energy changes or enthalpies associated with vaporization and sublimation. And I'm not showing them on this slide, but the reverse processes like condensation, freezing, deposition, those are all going to have enthalpies that are the same magnitude, but opposite in sign. If we look at our familiar example of water, we can get a sense of the size of these different transitions. So we see that the enthalpy required, the heat required to melt 1 mole of ice, convert it from a solid to a liquid, is 6.01 kilojoules. The enthalpy of vaporization is considerably larger. It's 40.7 kilojoules. And the enthalpy of sublimation is larger still. It's 46.8 kilojoules. We could graphically show this, as we see here, and water is shown as the third from the left. The enthalpy of fusion, or the heat of fusion, is much smaller than the other two. And the reason for that is not too hard to understand, because if we think about fusion, we're not really separating the molecules from one another. We don't have to overcome all of the intermolecular forces. We just need enough energy that they can start moving around, sliding past one another. But if we were going to vaporize something, that is to transform it into the gas phase from the liquid, well, now we have to completely separate the molecules. So we have to break all of the intermolecular forces apart. You might also notice, if you look at this chart, that the enthalpy of sublimation is exactly equal to the enthalpy of fusion plus the enthalpy of vaporization. Right? And that kind of makes sense because we know enthalpy is a state function. So therefore, going directly from the solid to the gas should be the same energy change as going from the solid to the liquid and then to the gas. Now, we've been talking about water, but if we look at substances that are nonpolar like butane or have dipole-dipole interactions like diethyl ether, or even have metallic bonding holding the atoms together as they do in mercury, we can see that always we have the same order. The heat of fusion is smaller than the heat of vaporization, and the heat of sublimation is the largest. And in all of these cases, if you add up the first two, you'll equal the heat of sublimation. We can also then see that as the intermolecular forces are increasing or getting stronger, that these values get bigger. And that makes sense because to go all the way into the gas phase, we have to overcome all of these intermolecular forces. Well, we can do problems based on this concept, and we're going to do a couple during this lecture. Here's the first one. Let's imagine that we have an ice cube, solid water, and the dimensions of the cube are 3 by 3 by 3 centimeters. We've also got here the density of ice, which is, as we learned a couple of lectures ago, a little bit smaller than the density of water. And then we're given the enthalpy of fusion. So to do this problem, we just need to know two things. We need to know the number of moles of water, and then we need to know the enthalpy of fusion. Now we're given the enthalpy of fusion, but we have to calculate the number of moles of water. We can start by calculating the volume of this cube, 3 by 3 by 3, so its volume is 27 cubic centimeters. If we now take the volume and multiply by the density, 0.91 grams per cubic centimeter, and then divide by the molar mass, 18.01 grams per mole, we can determine that we have 1.37 moles of water. So this is a little bit of a review of the kind of problems that we did back in Chapter 1. Not so bad as we're getting close to the final exam to see these kinds of problems again. Now that we know the number of moles, well, it's really easy from here because the heat that you have to put in to drive a phase transition is just the number of moles times the enthalpy of that phase transition. Here we're dealing with fusion. So if we take 1.37 moles times 6.01 kilojoules per mole, we get 8.2 kilojoules. In that last problem, we were just dealing with converting ice to water, but we started actually at the melting point. We can do somewhat more complicated problems where we might have to heat or raise the temperature to get to a phase transition, and then we could go through a phase transition. This gives rise to something which is shown here, which we can call the heating curve of a substance. This is the heating curve for water. So what's shown on the y-axis would be the temperature of the substance, and what's shown on the x-axis is how much heat you need to add to move around on this curve. Notice that if you were going to have, let's say, water at room temperature, and you added heat to it, you added energy to it, it would get warmer. The temperature would go up, and it would go up and up and up until you hit the boiling point. Once you get to the boiling point, if you add more heat, the temperature does not go up. Because what's going to happen at that point is the heat you're adding has to be used to break apart the molecules. That consumption of the energy you're inputting prevents the temperature from rising further. So we see that when we're at a phase transition, we get horizontal lines here because the temperature doesn't go up. Now the equations that we might use to do these calculations are either, let's say when we're on one of these blue lines, A to B, C to D, E to F, right? On those lines, the heat that goes in is just going to raise the temperature of the substance. And going back to Chapter 5, we learned about specific heat. So the amount of heat added is going to be equal to the specific heat, C sub S, times the mass, times the change in temperature. But when we're on these red lines, these horizontal red lines, that's when we're changing phases, right? So on line B to C, we're going to do a calculation like we just did on the last slide, the number of moles times the enthalpy of fusion. When we're on the line D to E, we're we're going to calculate the heat using a very similar equation. The only difference is now we're taking the number of moles times the enthalpy of vaporization. Okay, so let's illustrate this with a problem. Here we're going to take 22 kilograms of liquid water. That's about 5 gallons or so. One of my hobbies is home brewing, and one of the things you have to do is heat water when you're doing that, and this is about the amount of water you would heat in that process. We're going to heat it from 25 degrees C, where it's a liquid, to 125 degrees C, where it's a gas. And we want to calculate how much energy we need to put in to make this process happen. So the specific heat of water is given here, liquid water. When it is either ice or gas, you have a different specific heat. And the specific heat for water vapor is 1.84 joules per gram Kelvin. And we know from our earlier slides that the heat of vaporization is 40.67 kilojoules per mole. Okay, in step 1, we want to heat the water from room temperature, 25 degrees C, up to the boiling point. On our heating curve, that would correspond to going from this point up to point D. Okay, so I told you on the last slide, we are just going to use the specific heat equation from chapter 5. And it's just simply a matter now of plugging in the variables. We do need to calculate the mass before we can go any further in grams, because the units of specific heat require it to be in grams. So 22 kilograms is 22,000 grams. Plugging that in, 22,000 grams times the specific heat of liquid water times the change in temperature, 75 degrees, right, because we're going from 25 to 100. That will allow us to calculate that we need 6.90 times 10 to the 6 joules. 6.9 million joules. If we were going to convert that to kilojoules, it would be 6,900 kilojoules. That seems like quite a bit, but then again, it is quite a large volume of water. Okay, now that we've reached the boiling point, we need to calculate how much energy needs to be added to separate all of those water molecules in the liquid state into a gas. Okay, so we're going to vaporize or boil the water. And that is on our heating curve to go from point D to point E. So this problem is very much like the one we just did. We need to start by determining how many moles of water we have. And we can do that by taking our mass, 22,000 grams, and divide it by the molar mass, 18 grams per mole. And when we do that, we get 1.22 times 10 to the third moles of water. Then we just need to take that number of moles and multiply it by the enthalpy of vaporization. And doing so, we get this number, 49,700 kilojoules, which is actually a much bigger number than the amount of heat required to raise the temperature from 25 to 100. But we might have anticipated that from our heating curve, because the amount of heat added is the x-axis. And you can see that to go from point D to point E, we traverse quite a ways on our x-axis. Okay, now that we're at point E, the last step is going to be we want to heat it, this gas, to 125 degrees C. To do that calculation, here's where we're going on our heating curve. We're going to finish right here at the top of our heating curve. We're going to go back to our specific heat equation. We already know the mass of our water, which doesn't change when it's in the vapor state as it would be in the liquid state. And so the only difference is the specific heat of water vapor is lower than that of liquid water. And our temperature change here is now just 25 Kelvin. So when we do the multiplication, we get basically 1 million joules, 1.01 times 10 to the 6 joules, or 1,010 kilojoules. So finally, if we want to calculate the total amount of heat added on this journey, we just have to sum up the amount of heat added at each step. And so that's going to be 6,900 plus 49,700 plus 1,010, and we're going to get 57,600 kilojoules of heat would have to be added to transform this amount of water into steam at 125 degrees C. So I think you'll see some problems like this in the homework. Each step is not really that hard, so it's just a question of thinking about what happens on a step-by-step basis. Okay, there's one more phase of matter that we should discuss before we leave this section, and that's something called a supercritical fluid. What exactly is a supercritical fluid? So if you were to take a gas and apply pressure to it, compress it, what would generally happen is that gas might transform into a liquid. And how would you know the difference between a liquid and a gas? Well, we know that a liquid is not very compressible. It has a much higher density than a gas. We know that it has a surface tension, right? A liquid would have a surface. And there might be vapor above the liquid, but there would be a distinct divide between the liquid and the vapor. A liquid would not fill its entire container. And a supercritical fluid is one that has the density of a liquid. In other words, the molecules are as close together as they might be in the liquid state, but they don't still stick together quite like a liquid. They flow like a gas. They fill their container. If you had a supercritical fluid inside a container, there wouldn't be any divide between the liquid and the gaseous state, okay, because those states wouldn't exist. Instead, you would have a supercritical fluid. So supercritical fluids are like gases in some ways, but a little bit like liquids in how densely packed the molecules are inside the supercritical fluid. For any given substance, we can talk about something called the critical temperature. Above that temperature, it is not possible for a liquid to exist, right? So if you were to compress a gas or any substance above its critical temperature, you would not be able to get a liquid. You would just, at some point, compress it so far you would get a supercritical fluid. And the pressure needed to compress the liquid right at the critical temperature, we call that the critical pressure. If we were to look at this table of critical temperatures and pressures of different substances, what we would see is that as the intermolecular forces get stronger, right? Let's look at these substances at the bottom, water and ammonia, which can do hydrogen bonding, have relatively high boiling points. And then the substances at the top are these small diatomic molecules or even noble gases, which have quite weak intermolecular forces. But it's interesting to think about something like nitrogen or methane, that at room temperature you could never have a liquid. If you compressed it, trying to squeeze it down until it became a liquid, you would instead get a supercritical fluid. Carbon dioxide is quite an important supercritical fluid because you can see the critical temperature is not that much above room temperature, and the critical pressure, 73 atmospheres, pretty high, but achievable. Actually, in industrial applications, people use supercritical carbon dioxide. So, for example, you can use supercritical carbon dioxide to extract caffeine from coffee beans. So you can decaffeinate the coffee using supercritical fluids. You then run that supercritical fluid through a filter to separate out the caffeine from the CO2. And then the leftover CO2, you can just basically reduce the pressure and it just goes away as a gas. You can also use supercritical CO2 extraction for getting things like fragrances out of flowers and extracting other sorts of volatile aromatic molecules. Okay, well, we'll come back to supercritical fluids when we talk about phase diagrams in 2 sections down the road.